Okay, this is part 2. We're looking at counting techniques, and we just looked at the idea of a permutation, the formula right here, and we want to find 4 permutations of 0. So again, the formula would be 4 factorial divided by 4 minus 0 factorial, which is 4 factorial divided by 4 factorial, which actually is just 1. Here's how you can calculate it. There is in your calculator, if you can find an NPR button, a lot of times you do like NPR and then 4 comma 0. Some will have you do 4 and then type in the NPR button and then do a 0. But calculator should have that. StatCrunch also has it. So you're going to go under Data, Compute an expression, build an expression. And you're going to be looking for something that looks like permutation. And there's a perm, so we'll go with that. And then I would type 4 and 0 and click OK and compute. And you can see that it spit that out for me right there. So that's how we're going to use StatCrunch. But again, your calculator most likely has it. It's probably a little bit easier to do it in your calculator. Now let's look at the Indy 500. So suppose that you have 40 cars that start the Indianapolis 500. In how many ways can the top 3 cars finish the race? Okay, so in this case we've got 40 things to choose from, and we're looking at how many ways can we order 3 of them, where again the order matters, because if you're standing first in line, that's very different than if you're standing third in line. Because first place is the winner, third place is taking third place. So order is going to matter very much here. So this would be 40 permutations of 3. And again, I'll just jump over here into StatCrunch. And we'll do stat, compute, expression, and then we'll build it. We're going to find permutation, or perm. Again, if you found in your calculator, it's probably way faster than this. But just so you can see a place to do it, so we do 40 comma 3. Click OK and compute. So you get 59,280 different ways that that you can do this. So 59,280 different outcomes that could occur. Whoops, I'm in the wrong page. There we go. That could occur with that top 3 finishes. So that's permutation. Next, we look at a combination. And combination is a collection without regard to order. So combination order does not matter. Okay, we're still looking at R objects that are chosen from N distinct objects. R's got to be smaller than N, and there cannot be repetition. So the symbol NCR represents the number of combinations of N distinct objects taken R at a time. So now let's go back to our example where we had letters A, B, C, and D, and we want to know how many combinations of 2 exist. Okay, well, we have AB, we've got AC, we have AD, we have BC, we have BD, and we have CD, and then all the others would just be repetitions. So like BA doesn't come in here, DC does not come in here, because the order doesn't matter, whichever comes first or whichever comes second. So notice that we get 6. So this would be 4 combinations of 2. Okay, and here's the formula for combinations. Okay, it is 4 factorial, so it's right down here. So it'd be 4 factorial divided by R factorial, which is 2 factorial, times 4 minus 2, n minus R factorial. Okay, so this would be 4 times 3 times 2 times 1 over 2 factorial is 2 times 1, and then 4 minus 2 is 2 factorial, so that would be 2 times 1. And you get this cancellation, and 2 times 3 is 6. Okay, so notice that we take out the repetitions, so combinations are going to be smaller than permutations because we don't have to take into account all the different orders. Okay, but again, the only distinction we're looking at combinations, the formula changes a bit, and that's because order is not important. Order does not matter. But the rest, having different arrangements of R objects from N objects, that still holds the same. So now we want to find 30 combinations of 4. Okay, so if we're going to find 30 combinations of 4, again, this would be 30 factorial over 4 factorial times 30 minus 4 factorial. Okay, this is going to be big. But I just want to show you one nice thing about the factorials here. So this would be 4 factorial, and this is going to be 26 factorial. Okay, this is kind of cool because you do 30 times 29 times 28 times 27 times 26. I'll stop there, but it keeps going down. And then you'd have 4 factorial times 26 factorial, which is 26 times 25 times 24, and so on. And the 26 cancels, the 25 cancels, the 24 cancels. That goes all the way down. So you get tons of cancellation going on. So it's just really nice how this works out. It turns out that this number is 27,405. And notice that it's much smaller than, I believe, the 50-something thousand. Or no, that's a completely different problem. Sorry, I was in the wrong realm there. You can do it in StatCrunch. So you're going to do data, compute an expression. In this case, you're looking for combinations. So there's combinations, and you would do 30, 4, and compute. And you can see the 27,405. Okay, but again, in your calculator, you're looking for an NCR button. You'll either do NCR 30, 4, or a lot of the scientific calculators, you type, not a P, you'll type 30 and then the NCR button and then 4, and it will spit out this number right here. Okay. All right, so in this question number 52, we're looking at simple random sample. How many different simple random samples of size 7 can be obtained from a population of 100? Okay, so we just want to know, you want to randomly select 7 people out of 100. The order doesn't matter. It doesn't tell us anything about the importance of someone being first or fifth. Whether you're picked first or 7th, it doesn't matter. So order does not matter. And if order does not matter, then we use combinations. So this would be 100 combinations of 7. And again, these numbers are going to be massive when you get this big. So 1.60076 times 10 to the 10th. So we're in the billions here. Don't be trying to calculate these things by hand. It's just messy. But that is combinations. So again, very similar to permutations, except for combination, the order does not matter. Now we want to look at permutations with non-distinct items. I mean, you can't differentiate. So let's suppose, you have, just for a formal definition first, the number of permutations of n objects, of which n1 are of one kind, n2 are of a second kind, up to nk. And n is just the sum of all these numbers. I know this looks kind of messy, but the way you find it is you do n factorial and then you divide it by all of the different objects. So let's just do an example here with, how many different ways can you order the letters Mississippi? Now notice we've got all kinds of overlap. You have 4 S's. How can you distinguish which S is the first? It'd be hard to say, okay, this is the first, second, third, and fourth S. You can't distinguish that. We don't write, like subscripts or anything for our letters. So what we do is we say, okay, we've got, in Mississippi, there are 11 letters. So that's going to be our N, 11 factorial. Then you divide that thing by, okay, and then you just look at the letters. M, how many different M's are there? There's 1. So that would be, we do 1 factorial. So this is kind of like the N1. Then the next letter is I. I count in there 4 i's. So then I would divide by a 4 factorial. That's for all of the i's. And then s, there are also 4 s's. Sounds like Wheel of Fortune. Okay, 4 factorial for the s's. And then there are a couple of p's. And notice that these should add up to 11. So 1 plus 4 is 5, 9, 11. So those should add up to 11. And then now if I do this calculation, I would get 34,650. So there are 34,650 different ways to order the letters in Mississippi that would look different. And that takes away, you know, the whole, okay, well, this was the first S, this was the second, the dividing out, this takes out all of those ambiguous cases of, okay, what is first, what's the first S, what's an S is an S in this case. Okay, so now we're going to look at some probabilities. Okay, so this is where all the idea of counting is leading up to, is with the probabilities. So we want to compute probabilities involving permutations and combinations. So we've presented some counting techniques in this section, you know, there are some classical methods, some specific methods, permutations, combinations, so forth. And so let's recall that this method stated the probability of event E is the number of ways E, or event E, can occur divided by the number of different possible outcomes. And that's where counting comes in place when we're trying to find a probability, is you know, how many ways can something occur, and how many ways can this particular event E occur out of all those different possible outcomes. And that's where we're going to create or calculate this combination, or excuse me, not combination, this probability. So let's look at a garage door code. So outside a home, there's a keypad that will open the garage if the correct 4-digit code is entered. I'm sure many of you have experienced this. You have to type in your 4-digit code, and then you're able to get into your garage. So how many different, part A, how many different codes are possible? Well, you've got 10 choices, so you have the letters, or the numbers 0 through 9. So you have 10 for the first, 10 for the second, 10 for the third, 10 for the fourth. So this would be 10 times 10 times 10 times 10, which will give you 10,000 different choices. So then, what is the probability of entering the correct code on the first try, assuming that the owner has no idea what the code is? So what's the probability that you guess this thing right on your first try? Well, you have one guess out of the 10,000 different possibilities, which is quite small. And so the likelihood that you go up and you just guess the password is 1 in 10,000. So that's a basic example there. Okay, now Social Security number. So Social Security number is used to identify each resident in the United States uniquely. The numbers are of the form you can see there: 3 numbers, -2 numbers, -4 numbers, where it can be anything from digits 0 to 9. How many different Social Security numbers? Okay, so you have 3, 4, 5, 6. There are 10 different slots. So it'll be 10 times 10 times 10, or 10 to the 9th power, because again, you'd have 10 for the first, 10 for the second, third, fourth, fifth, sixth, seventh, 8th, 9th, 10th. All those would have 10. So it'll be 10 to the 9th power. Well, I'm not going to write that down, but so 10 to the 9th, different numbers. Okay, what is the probability of correctly guessing the Social Security number of the President of the United States? So what's the probability that you guess that thing on the first try? Well, you have one guess out of the billion different numbers, so pretty small chance. But that's just a basic look at calculating probability. So that ends this lesson. If you got any questions, let me know. But again, counting techniques are going to be huge when you're looking at probability. And I will just say, again, permutations, order matters. Combination, order does not matter. Make sure those things are locked in. Let me know if you have any questions.